Okay, folks, this is section 8-1. This is recording number 3. All right, so now this is the foundation of everything. The hypothesis testing, giving you these errors, that's kind of mechanical, okay? I just need you to make sure that you carefully read this section up here that I just went over with you. And it's almost the essence of it right here, okay? Uh, Talking about this mean pulse rate and how do you make a decision? The mean is computed from the data that you get. You compare it to a population mean. You make a decision. It's all based on the statistics involved. That's the essence, okay? So make sure you read this material. In your textbook, it starts at the bottom of page 416 and it goes a couple of pages, about 3 or 4 pages. So make sure you read that carefully. If you have any specific questions, send me an email. I'll be happy to do another video. Okay, so we got the different types of errors that we're talking about. So when we're talking about errors, as we've just mentioned, we have the 2 different types of error. The type of error that we're going to be primarily concerned with is beta, okay? Okay, and let me bounce back up here. I don't like this example of the jury trial for a variety of reasons, but the language here is actually very helpful, okay? All right. About very few things in life, anything relating to human affairs, even things relating to science, it's impossible to say that something is absolutely positively proven because human beings are doing the measurements. It's just, you can't do it, okay? So you have to make the best decision you can. So you're making the decision based on probabilities. If there's a large difference between the mean obtained from the sample and the hypothesized mean, the null hypothesis, well, the null hypothesis is probably not true, okay? But how big of a difference is necessary in order to reject the null hypothesis? When do we decide this, okay? If we have to have some rule, or the Federal Drug Administration would never approve medications. We'd say, well, we don't know. But you got to have these medications approved. People will die without them. So we have to have some risk. We have to allow for some error. We have to accept that there's going to be error. So what do we use, or what concept do we use? We use the level of significance. That's the maximum probability of committing a type 1 error. Okay, that's my so-called alpha. All right, I may have said beta before. I apologize. It's the type 1 error is alpha. Okay, and the reason we use alpha is because it's too hard to calculate the beta. The type 2 error is too hard. But type 1 we can do. Type 1 error is where we, oops, go back up here. Type 1 error is where the null hypothesis is true, but you reject it. And the reason you reject it is because the sample that you picked is so far different from the null hypothesis mean, as an example. It's so different from the null hypothesis that you say, oh my goodness, that could not possibly be due to chance. It must be true that Wheaties helps you do push-ups. Or it must be true that the pulse rate went up. It couldn't. I don't think that could have been caused by just mere chance, but it could have been, and you made a mistake because the null hypothesis is not false. The null hypothesis is true, but you rejected the null hypothesis. Okay? Well, that's going to happen some of the time. How often does it happen? That's your alpha. That's your type 1 error. Okay? So normally what we do is we say, well, we want to be wrong. We want to be wrong maybe 10% of the time at the most, but if it's really important, make it 5% of the time. But if it's life and death, make it 1% of the time. That's when we're going to make, that's the error that we're going to allow ourselves, okay? So if you were talking about Wheaties, does Wheaties help you do push-ups? You can be wrong 10% of the time. Who cares? 5% of the time might be something more significant, like something is really important to you for one reason or another. 1% of the time might be where you're saying, hey, is this medication safe, or will this medication kill you? Well, we don't think it will, but we're okay if we're wrong 1% of the time. That's kind of the concept here, okay? All right. So those are the typical error. Those are the typical levels of significance that we use. Okay. All right. So we decide what level of significance we're going to use. You decide this ahead of time in this technique anyway, the traditional technique. You decide ahead of time. You say, well, I'm going to accept an alpha of 5%. Okay. Then after you pick the significance level of, say, 5%, then you pick a critical value out of the appropriate test, okay? So for example, if you use the Z test, the Z table is consulted to find the appropriate critical value. The critical value determines the critical and non-critical regions. So this is all very algorithmic in the sense that you decide ahead of time certain things, what kind of tests you use, what kind of level of significance you want, what's your null hypothesis, and so forth. You decide all that stuff ahead of time, but once you decide that, then everything else comes from those decisions. Okay, so the critical region is where we say, okay, we're going to reject the null hypothesis. The non-critical is where we do not reject the null hypothesis. And then the critical value is that number. It's like a boundary. It separates. That's what we call the critical value. It separates the do you reject or do you not reject, okay? So it talks about whether it's a one-tailed test or a two-tailed test, okay? So in situation B that we had up above, the chemist was interested in increasing the lifetime of automobile batteries. Okay, the alternative hypothesis, the research hypothesis is that mu is greater than 36. Okay, so it's going to be rejected only when the sample mean is significantly greater than 36. So we'll see some examples here very shortly. Okay, so we have a one-tailed test. We can have a one-tailed test is either right-tailed or left-tailed, or we can have a two-tailed test. Okay, so the typical scenario is like right here. To get the critical value, the researcher must choose an alpha level. How often are you allowing yourself to be wrong? So, for example, alpha is equal to 0.01. So this is what you're saying here is it's a right-tailed test. So if by random, if I get a sample mean that's over here in this area, I am going to reject the null hypothesis. That's my critical region. That's this is my critical value here. If I'm over here, I'm going to reject the null hypothesis. But wait, you could be over there just by random chance, and the null hypothesis is true. So you will be wrong 1% of the time. But that's okay. That's just that's human. That's just life. You're going to be wrong some of the time. So you decide what that critical value is by looking at the Z value in the tables. Okay. So what you do is you go to the tables, and this is kind of an abbreviated version, but you got the tables in the back of your book, and you find out, okay, what's the critical value for Z? For what value of Z is it only 1% to the right, and is it 99% to the left? Well, you go down the Z table, you get 2.3, you come over here, 2.33 gives me an area under the curve, this area in the table, area under the curve, to the left is 99%. So 99% is to the left, 1% is to the right. So 2.33 is my critical value that I'm going to use. Okay. So he walks you through that here. So if you don't do this, if you don't take my advice, I'm just telling you, you're making a big mistake. Draw these cartoons. Draw the cartoons. It will help you understand this. So you draw your cartoon. Here's your zero. Mu is equal to 0. Remember, it's 0 because we're using Z variable. We're using the Z scores. The mean of the Z score distribution, the mean is 0. So that's why this is 0. So if the critical value is Z score of 2.33, if you're to the left of that, you do not reject the null hypothesis. You say, hey, this could have happened, this sample value, what I got, my X bar that I got, that could have been just due to random chance. Just so happens that I got that value. But if I'm to the right of 2.33, then I'm going to reject the null hypothesis. I'm going to say, hey, wait a second. I am so far beyond the critical value that I'm going to reject the null hypothesis. It must be true that my whatever I'm looking for, let's say it's the mu that I'm looking for, it comes from a distribution that does not have the same distribution as is in the hypothesized distribution. Okay. All right. So he's got all these different scenarios here. You got to spend the time looking at them. Okay. It doesn't do any good to watch me read this to you. You've got to get your pencil and paper out and draw your cartoons and make sure you understand why this is all true, why this is the way we're doing it. So let me bounce down to the two-tailed test. You know, a two-tailed test, you know, what you're saying is, hey, listen, I can be wrong. Alpha, okay, it's a two-tailed test. So if I'm over here or if I'm over here, I am going to be rejecting the null hypothesis. So this would be in a scenario where you say, you know, that pulse rate is not the same. I don't know if it's more, I don't know if it's less, but it absolutely is not the same. That's my alternative hypothesis. Well, if I end up over here, I reject the null hypothesis. If I end up over here, I reject the null hypothesis. So that's why we call it a two-tailed test. I can be wrong over here, I can be wrong over here. Okay? Makes sense, right? What is the critical value? Well, this one's a lot harder to find, okay? It's harder to find out what those critical values are. But the concept is very, very simple. If you think about it, if my alpha, I call it the budget. If my budget for error, if I'm allowing myself to be wrong 1% of the time, then half of the area is over here, half of the area is over here. So half of my error budget is over here. That's half of a percent, that is 0.005. Half of it's over here, that's 0.005. So these are the two critical values that I need. I need z and negative z. Well, it's easy enough to find because I got the table to find the z, the positive z, and the z distribution is symmetric. So once I find this one, I automatically know what this one is, just the negative of it. Okay. So I got to find the critical value right here such that to the left is 99.5% of the distribution. Only half of 1% is over here. So how do I find that? I go to my table and I find it. So he's basically telling you right where it is, but look it up yourself. You got to look this stuff up yourself to learn how to do it. Okay. All right, so it tells you how to do it right in there, okay? Okay, and this one actually falls between two different values, so you can use either one of these. Okay. All right, so now we've got the critical values. We're gonna use plus or minus 2.58 is plus or minus because it's a two-tailed test. Okay. All right, so I'm telling you, draw the cartoons, put in the critical value, shade in the critical areas. It will make life so much easier for you. So here's some examples here of how this is going to work. Okay. This would be a good page for you to photocopy or write down the information, because what he's basically doing here is he's saying, hey, I'm going to choose three different alphas, three different error budgets, 10%, 5%, and 1%. And I'm going to give you what the critical value is for each one of those. Okay. So all you have to do is have a copy of this somewhere, your cheat sheets. And if you know that it's, for example, you know, a two-tailed test, and you know that alpha is 0.05, you know what the critical value is, plus or minus 1.96. It just makes it easier. That way you don't have to look at the tables. I guarantee you, guys that do this for a living, that's what they do. Okay, so here's the procedure. Here's how you find those critical values. We're going to have to do an example here. So let me stop the tape right now. When we resume, we'll go to example 8-2.